Good morning. Our first speaker today is François Loeser on a non-archimedean Ax-Lindemann theorem.
Okay, thank you. So it's a great pleasure to talk here. So there are two important pieces of information on this slide. First one is that my institution changed name. So please keep this information in mind, because who knows what the name will be next year. And the other one is some advertisement for the French bid to host the ICM 2022. You can find information on the website and a very active Twitter feed if you are interested. Sorry? Okay. So something wrong. It should be written that this is Jean work with Antoine Chambert-Loir. So before explaining what is non-archimedean Ax-Lindemann, I should start with okay. Quelque chose à voir? Merci. Okay. So I should start by reminding you of the standard Lindemann-Weierstrass theorem. So it's a statement in transcendental number theory. So you start with an algebraic number that we assume to be linearly independent over Q. Then the exponentials are algebraically independent over Q. There is a geometric version due to Ax. So you consider now it's a functional analog, so you consider the exponential functions on n variables from Cn to C star n. And this geometric version states the following. So you start with some irreducible closed algebraic subset of the target space. You take the preimage under the exponential mapping, so which is a transcendental function, so you get something analytical. And inside, you take a maximal irreducible closed algebraic subset, W. And then such a W is of a very special form. Namely, it's translate by complex number of a linear subset defined over the rational number. So, that's to say that it's defined by linear equation sigma of alpha I xi is a complex constant with alpha I is a rational number. Okay, so this statement is not the original form of Ax result. Originally, Ax statement was a statement in differential algebra, but it's not difficult to check that this statement is equivalent to Ax's original theorem. Now, an hyperbolic version of Ax's theorem is due to Pila, so I will state it in the simplest possible form. So Pila proved more general statements, and then it was very much generalized by a bunch of people, which I will quote in a few seconds. So you start with Poincaré upper half plane. You have the modular function J from H to C. And as we did on the previous slide with the exponential function, we consider the function induced by j on each component. And then Pila proved a rather formally similar statement. So you start with an irreducible closed algebraic subset of the target space Cn, and you take a maximal irreducible closed algebraic subset W. I will maybe say a few words later about what I mean by irreducible here. And then W is very special, and here special is there are two kinds of equations. So either some coordinate is a constant, or you have two different coordinates, so k and a should be different, and they are related by an element of PGL2 over Q. So that's the Pila theorem. And so this is a very different nature of Ax theorem in the sense that, as far as I know, there is no proof in the realm of differential algebra. You have to use different techniques which were introduced by Pila and Zanier, relying on the Pila-Wilkie theorem. And this was largely generalized by Pila and Lindemann, also Peterson and Tarchenko. And one of the ultimate version is due to Klingler, Ulmo, and Yafaev. So in a very general setting. And as many of you certainly have already heard several times, I mean, this is a key ingredient in Pila's approach to Andr conjecture. I will not talk about this today. And so the aim of my talk is to present a periodic analogue of this theorem of Pila. Okay? So we should find, so typically we have, in the previous statement we have two spaces X and Y, where you can give a meaning to being algebraic. So maybe they are not algebraic, but they could be just domain, analytic domain, but they are naturally embedded in some algebraic variety. And you have a highly transcendental map, and you want to understand when what are the maximal the maximal algebraic subobject of three images of algebraic object from Y. How special they are. So in the periodic mode, we have first to find situations of this type, and one of the easiest non-trivial comes from Mumford's theory of periodic uniformization. And so the setting is as follows. So you start with the finite extension of QP, F. Okay, F could be QP for the whole talk. I mean, it would not change much. And you consider subgroups gamma of PGL2 of F. So they are called Schottky groups. So they are discrete, torsion-free, and finitely generated. And in fact, Liara proved that these subgroups are always free. Of course, free of finite type. And we will introduce a condition which is very important in our approach. An arithmeticity condition. So I'm very sorry for this terminology because there is a classical notion of arithmetic subgroup, and this is different meaning of arithmetic. And so gamma is in PGL2 of F, but okay, we will say it's arithmetic if it's in fact the matrices of elements of gamma can take the value in some number field contained in F. Okay. Now we want to have gamma acting on the projective line of say CP. CP is a completion of the algebraic closure of PP. But it's good to have a non-est action, so we better take care of the limit set. So what's the limit set? So it's written here. So you take you take some point of P1, a CP point. You take different distinct elements of the group gamma, and maybe you get a limit. And so this will be a limit point. And so you consider the set of this limit point, and it's closed, and it's also perfect as soon as the rank of gamma is at least 2, and we will always assume that the rank is at least 2. And then you remove this, and you get domain omega. But then I did not write P1 of Cp minus L gamma for good reason, because I want to have an analytic structure on this space. And I will later draw a few pictures to explain how omega looks like. But what is important is that it is endowed with the structure of an analytic structure. So we will use the Berkovich framework, but this is not so essential. You could use any other, I guess. And this is a substitute for the Poincaré plane, so maybe I should explain this. An example of something which is similar is the Drinfeld plane. So you take P1 and you remove all the QP points. So this looks a bit weird the first time one sees it, and one does not see many planes in this picture. But one should remember that, okay, this is by analogy. If we were working over in the Archimedean world, it would be natural to do this. If one considers that QP is like the real number, then okay, this is not the P1 of CP, but not too far from it. And so let's do that. Okay, and this is we just get 2 copies of the Poincaré plane. So in this case, this is connected, so there is only 1 copy. And so that's a typical picture. I will explain a bit more very soon. And so it's a replacement for the Poincaré plane. And so a beautiful result of Mumford says that in fact now you have gamma. You may model now omega by gamma. It has a natural analytic structure. And in fact, there is a unique, smooth projective curve over your base field F of genus G. What is G? G is the rank of gamma, such that in fact omega discussion is an identification of X gamma. And you can say it in another way. You can say that omega gamma, you get a uniformization of analytic uniformization of your curve X gamma. And so this is this kind of map that will replace the exponential function or the j function in our setting. Okay. So we will consider a finite number of copies, but why there is no reason to ask that all these Schottky groups are the same, so we just take n different Schottky subgroups, but each of rank at least 2. And now we have take the products of the omegas and the product of the x's. And we have now uniformization morphism in dimension n from omega to xn. And we want to prove a statement similar to the one I presented at the beginning. And so we start to say, to express what are the special objects in this game. And here it's a bit, there's some artifact which is not so relevant, but difference between being irreducible and geometrically irreducible. So let's take some extension of f, and if I have a subset of omega. So, okay, what is an algebraic subset of omega first? So I view omega as embedded in a product of P1, so as a subset of an algebraic variety, and so I will consider traces of algebraic varieties in omega, and this will be called algebraic subset. And about irreducibility, then it's a bit more subtle. So there is a good, fortunately for us, there is a good notion of irreducible components in the non-archimedean world. I mean, it's highly non-trivial. I mean, there is work of Conrad and of Antoine Chambert-Loir on this, which we are very lucky to be able to use. And so we will say by irreducible algebraic, in fact, this will mean an analytical irreducible component of something algebraic. Okay. And so we will say first notion of special is what it's called flat. I mean, we are not responsible for this ugly terminology. I mean, so you have two kinds of equations, either as before, either z is some coordinate is constant, or two different coordinates are linked by an element of PGL2F over the field capital F. So here, if one can remark that it's a bit different than what we did so before, because before the matrix was in coefficient in Q. So one expects some rationality statement, but here it's a bit different. So the rationality property is what occurs in this definition of. So we say its stricter condition for W is being geodesic, and this corresponds to the rationality condition, and it's the fact that such a G, I mean, we require that the conjugate of gamma I by G and gamma J, so in such a situation, they should be commensurable. So by commensurable, we mean that each is a finite index in the other one. Okay? And so this is a stronger notion of being geodesic. Now I can state our main result with Antoine Chambert-Loir. So start with n Schottky subgroup gamma I, all of rank at least 2. satisfying the arithmeticity condition. So you have this uniformization map from omega, the product of domains omega gamma r, and x arm, which is the product of identification of curves, for curves. So I give two statements which are completely equivalent, but so the first one is you start with an irreducible closed algebraic subset of the algebraic variety X. You consider the preimage of its identification, take a maximally irreducible closed algebraic subset in the sense I made precise a few moments ago. Then, if you go to CP, then every irreducible component is flat. Or this can, in fact, this would all over just a finite extension of F. And an equivalent form is if you assume W to be geometrically irreducible, then W is flat. So it's the same statement, but I don't know which one is nicer. So. Okay. And as a corollary, we deduce. So here in this statement, we are not able to get better than being flat. So this was a condition. We did not have any condition on the matrices conjugating coordinates. And but we deduce a bi-algebraicity statement. So now I'll start from. So in the previous statement, we started from a subset of the target space. Here we start with a subset of the domain W. So close the algebraic subset. Assume it's geometrically reducible. Then you have the following equivalent condition. First, it's geodesic, so it satisfies the stricter speciality condition. The image is algebraic in the sense that it's directly closed. Okay, it's more precisely, it's the identification of the directly closed subset. And weaker statement, it's enough to know that the dimension of the directly closure of the image is the same as the original dimension of W. So this is an illustration of very general philosophy that if you have two different algebraic structures, so to speak, and objects which are algebraic for both are very special. Okay. So the idea of proof is just to try to do the same as Pilar, and we do exactly the same as Pilar, except that we have to change many things. So key ingredient in Pilar's proof is the very well-known theorem by Pilar and Wilkie. So if you have a subset definable in of Rn, definable in some O-minimal structure, and you take its transcendental part, which is the complement of all the semi-algebraic curve in it, and then you have very few, on this transcendental part, you have very few rational points of, in terms of when the height increases. Okay, and with Raf and George, we proved a similar statement, except that at the time we didn't know what is an analog of a minimal structure, so let's restrict to subanalytic subsets. And then you have exactly the same statement. So I will go back at the end of the talk on this to this theorem. And okay, so this will be of use in our proof. And okay, so we will use the height. And so this is why we require this arithmetic condition from the very start, because otherwise we have no way to proceed. And what is a bit funny is that we do very much like Pila, but it's not the same geometry. I mean, in Pila's proof, I mean, a key role is played by parabolic elements of PGL2, so given by upper triangular matrices with ones on the diagonal, and here it's very different subgroups. And we have at some point to use the geometry of these Schottky subgroups, which now I will try to explain on the blackboard briefly. So take some gamma Schottky group, Schottky subgroup. So here it's in one variable, and we have some limit set, and I will assume for simplicity that the response is not in the limit set. Yeah, the basic reference for this stuff is the book by Gerritsen and Van der Poel. And in fact, this hypothesis is very much hidden inside the book. So with Antoine, it took us some time to realize that they were using all the time this hypothesis. But so this is not for free, because L gamma could contain all the QP points. And you have no way to have this assumption to hold. This assumption always hold on some finite extent after some extension of scalar. So okay. And so the rank of gamma is G, so let's assume for simplicity that it's 2. And then you have both B1, B2, C1, C2, so in general you would have 2G balls. So closed balls are distinct. And you have, gamma is generated by gamma 1, gamma 2. And gamma 1 has following, so gamma 1 sends a complement of B1 to okay, and same for gamma 2, and also yeah, and also okay, so gamma 1, so to speak, put everything that's outside B1 inside C1, and gamma 1 inverse do the opposite, and same for gamma 2 and so on. And so we need to understand some fundamental domain in this game. So fundamental domain is just given by the complement of this disk. store this. So let's call it F. And now let's try to understand what's happened when we run iterate action on. And so yeah, so okay, so let's gamma 1 act, for instance. So gamma 1 sends a fundamental domain inside C1. And now you get 3 little balls inside, not 4, 3. And and this would be gamma 1 of F. Okay? Okay, you can do the same with gamma. So if you take not only gamma 1, but all the words of length 1 in the gamma 1, gamma 2, sorry, okay, yes. So take F1 to be F union this, and now F1 is just everything except all the small, the 12 small balls. And then if you iterate once more, and then you see, so you see that these nested small balls, they converge to the limit set. And if you look at this with the right glasses, you see very much the hyperbolic nature of this. Okay, so this is how it works, and it's quite easy to handle. And you also see that that omega, y omega has an analytic structure. I mean, okay. So now we consider not only one fundamental domain for a given gamma, but one for each gamma I, and we take the product. And so we start with W. So what is W? W is maximal irreducible, algebraic irreducible in the preimage of some V. So we assume that its dimension is, say, n, and we will consider a certain set of matrices. So we require that so G1, we don't say anything about G1, but the next n-1s are supposed to be the identity. And we have this strange condition which occurred first in Pila's proof. So you ask that the translate of W by G, if you intersect with this fundamental domain and with the preimage of V, is still of the same dimension M as W. So it's rather big. And so the heart of the proof is to prove that after some reduction, I mean, here it's explained in a couple of lines. In fact, it's the bulk of the paper, so it's very. That's the number of k rational points in R of AT is quite big. So it's bounded below by a positive power of t. K is fixed. K is fixed because I put K is the field. Yes, so it's a given. It's given a datum. Okay. And so how do we prove that this number of points is of height bounded is big? In fact, at the end of the game, it reduces to the fact that in the free group of rank at least 2, you have many positive words of length L, so namely G to the L, which is small when G is 1, but which is rather large when G is at least 2. Okay, this is really the key observation. After you have some work to do, but. And so this is very much like in Pilar's proof. And once you know this, you get the idea now is to use Pilar-Wilkie or its periodic version. And so we had this set R, and so we are looking at its f point. F is a periodic field, and it's easy to. Basic fact is that it's definable in the sense that it's subanalytic. Okay, and here it's there's a. It's not difficult, but there is a rather nice mixture of two notions of definability. The naive one on QP or F points, and the rigid theory of rigid analytic subsets. We have to use both because we start with objects which are analytic in the rigid sense. Okay, but fortunately, I mean they are compatible. So if you start with some rigid semantic subset in the sense of Lipschitz, and you look at rational points, you get subanalytic sets in the usual sense.
What is RF definable?
I'm sorry?
RF definable?
Yeah, just a sloppy way to say subanalytic. Sorry. Okay? And now we can apply the periodic Pilar-Wilkie theorem to this set. And knowing that it has many rational points, we get that it has a large stabilizer. W has a large stabilizer in a group gamma, and this should imply that it is special. Because this is the second part of the proof. You have to do some geometry to use this fact to prove it is special. And so, maybe not everyone is familiar with Pilar proof, so in this audience. So you have this W of dimension n, and you project, so you have x, which is but we project to something m-dimensional. So okay, after some manipulation, we can assume that it is the first xi, m xi. And the game in the definition of the set R, we were not doing anything on the first m-1 variable. I'm sorry. Not the first one, I mean, from 2 to n, okay? And this amounts to freezing to freezing, when you project here, to freezing all coordinates, all components except the first one. So you play with in dimension 1, so to speak, with parameters. And so we perform an addition on the dimension m. And in dimension 1, we need to prove that you are special if you have a big stabilizer. And so this is provided by this very easy lemma. So, okay, you are in characteristic 0, and you start with a curve integral in P1 to the power n, having a smooth rational point. And so you consider its stabilizer, and also you consider its image when you project on the first coordinate. And you assume gamma 1, this image gamma 1 is big in the sense that it should contain some element of infinite order. Okay? Then situation is very constrained. Either the projection to the first component is constant, so not much happens there. Or P1 is just restricted to the curve. Is an isomorphism, and in fact the components of its inverse are either constant or negative. Or you have a third possibility that you have two rational points, 2 points in P1, which are, okay, 2 point subset which is invariant under the action of gamma 1. Okay, this corresponds to a ramified cover over 2 points. And the theory remark is that this possibility is excluded by the fact that or estimates on rational points. I mean that we have many that the set R is big, and so we can exclude the third possibility, and the first two are just nice to get our conclusion. Of course, there is some work to do because we have to pass from one coordinate, so to speak, with parameters. And so in Pilar's approach is okay, he uses lot analytic continuation and things like that. Here we have to be more careful because we are in a rigid setting. But at the end of the game, we are able to follow a similar strategy, even if sometimes the details of proofs are quite different. Yes? Yes, first projection, yes. I should have said that. Yes. We project on the first component. Yeah. Yeah. Okay. So in a few remaining minutes, let me return on the Pilar-Wilkie theorem. So over the reals, so you need the key. You have 2 steps. So you prove nice parametrization. So they are called Yomdin-Gromov parametrization. Even if in this context the existence was proved by Pilar-Wilkie. And once you have this, you use the determinant method to get the result. And so you need definable parameterizations of class CR and with a hold on the size of the derivatives of this parameterization. So this is what you need. So with Ralph and George, we do very much the same in the periodic subanalytic setting. It's the same statement, except that the GIs, okay, they're not defined on the whole ZPN, but maybe only on some definable subset. That's not a big deal. And we also have a version of a CT, of the Laurent series. Okay? But here the finite family GI has to be replaced by a definable family parameterized by some finite dimensional C space. Okay? But there was some issue here because you use the Young-Gromov parameterization via the Taylor formula. But here there is no Taylor formula, usually in the non-Archimedean setting. But you have the choice in the parameterization. So the key idea is to, at the same time you prove the existence of parameterization, you prove that they satisfy Taylor form. And so first application was the Pila-Wilkie for this statement. And another one that we obtained with Ralph and George was found for rational points of a CT. So it's a geometric version of the result by Bombieri and Pila. So you take some algebraic variety of the field CT of Laurent series. So of some degree d and dimension small n. And instead of counting points of bounded edge, which doesn't mean much because there are many of them. So I think the notation is self-explanatory. So CT index smaller than R means polynomials of degree smaller than R. So you look at points in X with in this with values in this object, and so you consider the Zaleski closure and the dimension of the Zaleski closure, and then you have a bound which is written here. So this dimension is bounded by R times n-1 and its dimension, and you have also the roundup of the quotient of R by D. So, and in fact, there is a triple bound which corresponds to linear spaces, which is Rn. I mean, but you see, as soon as the degree is strictly bigger than 1, this statement provides you a non-trivial bound, an improvement on the trivial bound. Okay, thank you.